Okay, hi everyone. So what I want to talk about today is continuing with the idea of higher order functions or functions as arguments from Monday's class. And in particular, there's really two things we'll talk about today. So one is writing some more higher order functions, and the other is solving problems by writing a pipeline of functions. Okay, and for the most part, we're going to go over the lab solutions or the equivalent of problems from the lab. So if you already got all the way through the lab and got all the answers, then you can probably skim through the videos pretty fast and skip and go right on to the homework. Okay, so if you remember our first example of a higher order function from Monday's class, the idea was map, right? So the idea with map was that if I want to add 1 to everything in a list, then I write map with the add 1 function, and that adds 1. If I want to double everything in a list, then I write map with the doubling function, and that doubles, right? So like I tell map, I would like to do this to every element of a list, and I give it a list, and it does that and gives me back the list of results, capturing that pattern. Okay, so the first problem in lab was to capture a different pattern. So we started with these two functions, which was the evens function, which says, given a list, give me back all of the even numbers, right? So it's always good to do some examples. Evens of 1, 2, 3, 4, 5 is the 2 and the 4. Evens of 1, 2, 3, 6, 4, 5 is the 2, the 6, and the 4, right? We're getting back the even numbers of the list in the same order as they were in the original list. Okay, so how do we do that? Well, if the list is empty, then empty. Otherwise, if we've got a head and a tail, we ask if the head is even. If so, we keep it. Otherwise, we get rid of it. And you've all more or less written this code in various guises, like the filter function from Quicksort. Okay, another example of the same pattern is keeping the uppercase letters in a list of characters. So if I have a list of the characters A and A and B, then the uppercase letters are just the A and the B. So char or char, however you want to pronounce it, is like string, except the strings have to be length 1, right? So it's just a single letter, which is useful because if you think of a string as kind of like a list, then characters are the elements of that list. And it's exactly the same style of code. What we say is that if you want to keep the uppercase letters in a list, well, you go through the list and you see if the letter is an uppercase one, and if so, you count it on, and if not, you forget it. Okay, so what's the pattern here? Well, if you give me a list of anything that is an A list, I'll give you an A list out, right? We're going to look for a function that's polymorphic that works for any type A, because here evens works for an int list and gives you back an int list. Keep upper works for a character list and gives you back a character list, and so on. And then we can kind of just copy the common bits of the two functions into something like that until we get to the point where we're asking case something of x of true goes to x cons filter x's, or false goes to filter of x's, right? So like the stuff that's common between evens and keep upper is that if the first element, we ask a question about the first element, and if the question comes back true, we keep the first element, and otherwise we forget it. So the thing we're missing is the question. So I can put another input here, question. And then the idea is that the question is supposed to be a question we can ask about X. And so the question, if it's something we're going to ask about X, and if in general we have a list of A's, then X is a single A, and the question is supposed to produce a true or a false, so it's an A to bool. So that's the structure of filter, right? We take in a question from A to bool, and if the question comes back true, we keep X, and otherwise we don't. And so, for example, now to test our higher order function filter, we can define evens as doing a filter with a particular question on L. And I need to remember to pass the question along into the recursive calls there. So what question are we going to ask about L? Well, here we have a name for it already, even P, so I can just say that. And so now if I ask for the evens in 1, 2, 3, 6, 4, 5, something like that, then I get the 2, the 6, and the 4, and we're good. And if I want to get keep upper L in character list, colon character list, right? Well, what are we doing here? We're filtering, and the question we're asking is a library function character dot is upper, which detects uppercase characters. And then I can do my same example, and that works. Okay, so the point is now I've defined filter. I don't need these instances of filter, those go away. Those were just like repeated code that I can get rid of now that I have filter and can just use filter to write the code that was morally an instance of filter. So in the lab, it asks you to revisit some of the quicksort stuff from before spring break, where we were writing out specific instances of filter with a rel argument that was LT or GT, which was really a less fancy way of just passing in the less than function and the greater than function themselves. Okay, so now what I want to go on to now is solving problems by writing a pipeline of functions. So let's suppose that for whatever reason, you want to write a function like add 1 less than 7, where the purpose is to add 1 to, let's say, find the numbers that are less than 7 in a list and add 1 to them. So, for example, if I add 1 to the numbers less than 7 in the list 1, 8, 7, 5, then I should get the 2 because that was less than 7, the 8 and the 7 go away, and then 6 from the 5 because I'm adding 1 to the numbers less than 7. And if we had just done this by recursion, well, you would say, okay, open up the list, look at the first element. If it's less than 7, then add 1 to it, and otherwise forget about it. Okay, so hopefully that works. Add 1 less than 7 of 1, 8, 7, 5 is 2 and 6. Good. Okay, so now if we think about this as a pipeline of higher order functions, what we can do is we can say, well, let me try and figure out how to solve the problem by chaining together ingredients made up of these higher order functions that we're now talking about, rather than trying to just do it straight out by recursion. So what you want to do when you're thinking about solving a problem as a pipeline of higher order functions is that you basically think of it as stages. And a good way to think about the stages of the problem is to think about an example. So if I think about starting with the example of 1875, then in step one, I could think that maybe what I do is I get the 1 and the 5. That is, I keep only those numbers that are less than 7. And then in step 2 of the pipeline, I would get my 2 and the 6. That is, for step 2, I would add 1 to them. So a good way to think about designing these kinds of pipeline examples is you take a specific example and you kind of work through the steps of what you might do. And so then the idea is that each step use of a helper function. So if I'm going to define this as a pipeline, then what I think about is I'm given L, and I think about how to do step 1. Okay, well, step 1 said to keep those numbers less than 7, and then I think about the higher order functions that I've thought about or know something about. Which one keeps numbers that are less than something? Let's filter. How do I tell it to keep the numbers that are less than 7? I feed it the function that says fnx goes to x less than 7, right? Which is the function that is true for numbers that are less than 7 and false for numbers that are not less than 7. Okay, so that's step 1. And then step 2 is then, in this example, to add 1 to them. So now I just think about, well, how do I go through a list and add 1 to every element of that list? Well, that's clearly a map, because map's the thing that goes through a list and does something to each element of a list, computing the list of results. So now if I do my example, okay, cool, I'm still getting the 2 and the 6. And another way to write this, if you want, is you could give names to the steps. You could say, let val step 1 be filter, step 2 be map that on step 1, in step 2 as my overall answer, and then that works too. Good. Okay, so it's kind of up to you which style you want to do things in. So you can either do the filter on L and feed that in as the list input to map just by writing it in the spot there. Or if you want, you can think of it giving it names and say, I'm going to do the filter on L, and then I'm going to feed that as the result to map. And either way that you want to do that, it's fine. Okay, so that was an example of number 1, writing a higher order function to capture a pattern, right? So filter is a specific pattern of computation where we're going through a list, asking a question of each element of the list, keeping an element or not, depending on how that question comes out. And then also writing some functions by a small pipeline here of 2 steps where we first do a filter and then do a map. And if you think about it, there's actually another way we could have done this. So maybe instead, I could organize my pipeline differently and say that if I start with 1875, I could in step 1 add 1 to all of the numbers, and then in step 2, we could keep all numbers that are less than 8 now, because we've already added 1 and we wanted all numbers that were less than 7 in the original list. And so if we wanted to do that, then now step 1 is doing a map to do that, add 1, and step 2 is doing the filter there. Okay, and that still works. So the idea here is that there can be many different ways to organize a pipeline, right? In this example, I can either first select the things that are less than 7 and then add 1 to them, or I could first add 1 to everybody and then select the things that are less than 8 now, and that accomplishes the same thing. Okay. So I think that's all on this example.